Awesome. Howdy, folks. Let's continue with some information and learning about refraction. In this video, we're going to kind of go over some of the basics, essential standards of what you should know about reflection of light, as well as how do you calculate these things mathematically. So you did a PhET simulation this week. You watched the first initial video. If you haven't watched that yet, watch that first, where this awesome teacher gives an example of using a car going through a swamp and a marching band, how light actually slows down in different mediums. And this all has to do with this new topic called refraction, which is the bending of a wavefront as the wavefront passes between two substances in which the speed of the wave differs. So now we're bending light as we're traveling from one medium to another. This bending of the light, as I just explained, is due to differences in the speed of light between your two different mediums. So the speed of light in a vacuum, remember, no particles, anything like that, and we represent speed of light with a c, is equal to 3.0 times 10 to the 8th meters per second, incredibly fast. It's usually slower in other mediums like glass and water. Once you're traveling through another medium, light's not able to travel as quickly as it does through a vacuum. So speed can change. Wavelengths can change in a medium. The only thing that does not change in the refraction of light is the frequency. So here's a little bit of an analogy. You have a car and you're going at a certain angle on a smooth road. If you're not paying attention, you start to veer towards the shoulder, and the shoulder, this is actually real, it's usually rough, and one of your wheels is starting to drag on the right side. This is going to make your car start to turn slightly to the right. This is the same exact nature of the refraction of light. Once light is passing through, let's say, a rougher medium than before, it refracts and it starts to veer in a different direction. So this leads us to, this is a law of reflection. It's the index of refraction, which we use the symbol n for a substance, is the ratio of the speed of light in a vacuum to the speed of light in that substance. And we get this equation. So the index of refraction, it's kind of this new idea, but what that tells us is basically how fast is something going to travel through that medium. So the slower the medium, the larger the index of refraction you're going to have. And each index of refraction is unique to that substance. So if you have a really big index of refraction, for example, like in a diamond, that's why they give you a little bling bling and they shine at you. A large index of refraction means that you're having more light that's being displayed in other directions, and when you shine it in a light, you get a little bling bling action. So this is a table that's on page 490 in your textbook. It's really helpful because it gives you a list of a bunch of indices of refraction for a lot of various substances. So for when you're talking about, you'll notice on this table for air, it's nearly 1. And the speed of light is nearly identical in air as it is to a vacuum. So subsequently, we're not doing super exact calculations in here. So we're just going to use for air, our index of refraction, we're just going to leave it at 1. But you'll also notice that the refraction it'll depend on the wavelength. And now different colors of visible light have different wavelengths. So this above table that you have right here is only accurate if you have a wavelength of light that's traveling at 589 Newton meters. So pay attention to that when you're looking through problems. And it should always give that to you is what it's traveling at, but just make sure that you're if it doesn't, then it'll give you a different indices of refraction. If it's traveling at 589, then you can use this table to look up what the refraction index is. So when light is passing from a medium with a smaller index of refraction to one that's larger, like let's say you're moving from air to glass, the ray is going to start to bend towards the normal. Now, some of the light is going to be reflected off. We're not going to focus on that. We're really just focused on what is the refraction. So you kind of see in this image, the light is traveling faster in the air medium. It's traveling slower in the glass. You have a larger theta, a larger angle in the faster medium, and a smaller angle in the slower medium. This means that the faster the medium you have, the larger the angle it's going to be away from your normal line. Now, to give you a little bit of a reminder, your normal is always perpendicular to whatever is doing the refraction or reflection. When light is passing from a medium with a larger index of reflection to one with a smaller index, like going from glass to air, you have a ray that's bending away from your normal. So you have your slower medium in glass, your faster medium in air. You have a smaller angle in the slower medium, a larger angle in the faster medium. So, as you kind of see in these laws of refraction on these last slides, let's look at a real example. Have you ever looked into a pond or a body of water and you think you're reaching towards something and you can see it, but if you actually stick your hands into the water, it's not grasping where you think it is? This is a real life thing that happens. Let's say you got a sweet cat that is trying to grab a fish in a pond. From the cat's perspective, it's looking down through a medium of air into the water. The light that the cat is seeing is then refracted in the water, and the cat sees the fish at a much higher angle than where the fish actually is. Same thing, the fish is looking up at the cat and it's like, oh man, you ain't gonna get me. And as the fish is looking up at the cat, it sees the cat at a much different position than where the cat actually is. This is because when you're in different mediums, the light is refracted and you can see an image that's in a different place than where an object actually is. So how do you know how much your light is bending? Well, lucky for you, there's a mathematical formula for that. And it's called Snell's law. Snell's law determines what your angle of refraction is. So here you have this equation. It tells you the index of refraction, n, in your first medium, times the sine of the angle of incidence. And remember, your angle of incidence is the ray that's going in, is going to be equal to the index of refraction of the second medium times the sine of the angle of refraction. It's hard to say these words. All right, so let's do an example. A light ray of wavelength 589, all right, we're good there. That's going to be working in my table. That's the optimal wavelength there. And let's say it's produced by a sodium lamp. And it's traveling through air, and it strikes a smooth, flat slab of ground glass at an angle of 30 degrees to the normal. Find the angle of refraction. So first we're going to identify what do we know, what don't we know. We know the angle of incidence to be 30 degrees. We know the index of refraction coming in is going to be 1 because it's traveling through air. Then you know your index for when it's traveling through the crown glass to be 1.52, and I found that on table 1 in my textbook. So now I want to know what is the angle of refraction. So I'm going to use my equation for Snell's law. I have a few reminders for you for how you rearrange an equation when you're using trigonomic functions. So I want to get theta r by itself. So what I would do first is I divide by nr, bring that over to my left side, kind of visualize it with me here. And then I have just sine of theta r left on the right hand side. You can't just divide by a sine. You have to do an inverse sine function. So that's where we get the rearranging of this equation. We get that theta r is equal to the inverse sine of the entire left side, where you have ni divided by nr times the sine of theta I. the entire inverse of that. So it's really important that if you're finding an angle, dividing by a sine doesn't mean anything. That doesn't exist. Dividing by a sine is like doing an inverse of a sine function of everything on the other side. That's a lot of memory from stuff we did last semester. So, if you have trouble with that, give me a ring. Come up onto Google Hangouts and I'd be happy to walk you through the math of how to do an inverse sine. But then once you do that math and you plug that into your calculator, you get that your next angle should be 19.2 degrees. So you're going to do 3 problems for homework today. It's page 493, number 1 through 3. I also suggest if you have any questions about what we've talked about today, reading through pages 488 through 492, just like 5-6 pages of reading there. It'll help you kind of solidify what we've talked about in these 2 videos. You can join in on Google Meets if you have any questions, and don't forget to be ready. Come Monday, join Google Meets right at noon, and you're going to come ready to pick your final project topic. So over the weekend, out of that list that I gave you guys, brainstorm your top 3 choices so that we can pick those all as a group on Monday. Other than that, you guys rock and have a great rest of your day.